Hi guys, welcome to the third lecture on model-driven engineering. I've been playing around with the sounds a little bit, see if it can get any better. Hopefully today's is not as bad as the previous two. So it's also going to be a bit of a short one. We're supposed to be doing one of these a day or so, but been a bit busy. So we skipped a few days, but let's try to get back on track, even if it's not a long lecture. So what we're going to do today is one of our first technical lectures. So we started off with just some kind of basic introduction. Today we're going to get a bit more into the weeds and try to understand a bit some of the technical concepts. It's also interesting to think about these things because these are not things we normally tend to worry about too much as software engineers, or at least not from this angle. So today we're going to talk about models and transformations. I think we might just stop around the transformations, I think. If we have enough time, we might get to problem space to solution space. Let me just put this on pause for a second. As usual, lots of stuff going on in the house. So as we were saying, let's double check we are recording, and we are a minute into it. So one of the key characters in model-driven engineering, and to be honest, he's not really a model-driven engineering person, really, but a person that thought quite deeply about models is Stachowiak, if you pardon my likely Polish pronunciation, presumably. So the book you should really read is Stachowiak's book, which unfortunately is in German. I have a reference to it somewhere around here. Here we go. So the book to read really is General Model Theory. And I'm actually dying to read this book, but unfortunately, the only version I could find of the book is in German. And I don't really speak German, so I didn't really think it was worthwhile buying the book and then trying to translate it and so on. It's a pretty hefty book as well. But this is sort of a very, very important book as far as modeling is concerned, as we shall see. And so Stachowiak, basically, the quote that we start our chapter with, the epigram, is that all of cognition is cognition models or by means of models. And in general, any human encounter with the world needs model as a mediator. So Stachowiak is already alluding here to this very broad notion of models. And the whole of the neocortex is, in effect, a modeling machine. We're going to leave the philosophical discussion towards the end of today's lecture, if there's a bit of time. But I think it's important to start with this kind of very broad idea. So as we said before, the fundamental equation of model-driven engineering is that models plus transformations are equal to software. And that's basically the MD take on Wirth's equation of algorithms plus data structures are equal to programs. And the first and most important thing of this equation is to try to define what we mean by model. So Stachowiak, when he defines what it is that we mean by a model, he said that there's three fundamental characteristics of a model. The first one is the notion of mapping. And the idea of mapping is that, if we go back to Derman's example, if you think of a model plane and if you think of an actual plane, you can imagine that we are mapping the model plane to the category of actual planes. So there's this idea that you can somehow map the entity that you're modeling to a set of the entities of the real world that are represented by this entity. Of course, we don't necessarily need to think of models of real things because we can actually model models. So the notion is that you can then start to recurse and create very complex constructions using this approach. The second characteristic that Stachowiak came up with or enumerated was reduction. So it wouldn't be no good if a model was as complex as the thing you're modeling, right? It would be a bit annoying if you needed to actually create a real plane in order to model a plane. So the idea of the model is that somehow we don't just map, we also reduce. We somehow reduce the complexity of the real world or the thing we're modeling, the object of the modeling, into just a subset of the properties that are of interest to the thing we're trying to deal with. And finally, and you probably will remember, we spent a lot of time talking about pragmatism. in the previous lecture. This is quite important. A model, because of this reduction property of a model, um, you must make a decision as to what goes into the model and what does not go into the model. And this has to be guided by pragmatism. So you don't just model something, you model something for a reason. And this definite purpose, this reason for you to do the modeling, is what guides you into this determining what properties are essential and what aren't. And you need to have a level of pragmatism. In other words, it's an empirical exercise um, rather than sort of an abstract formal exercise in which a certain level of judgment is required by the modeler into what should be part of the model. And these three characteristics are very important. And now, of course, if you think about it, model-driven engineering, the discipline itself, is in a way a model, which is why pragmatism is so important. So we discussed a lot about why it is it's so difficult for us to the terms within model-driven engineering are so fuzzy and so difficult and so and it is very, there are no formal definitions. But the reason for that is because model-driven engineering is in itself a model. Now, this may sound very, very confusing, but if you think about it, in order for you, the objective of model-driven engineering is to, or the solution space, again, a term we haven't defined yet, but the thing we're going to research on model-driven engineering is software engineering. We are trying, in a way, what model-driven engineering is trying to do is it's trying to construct a model of software, how the software engineering process occurs. And then it's trying to build on top of that model the domain, the domain they're interested in. So by necessity, we can't obviously have the whole of software-driven engineering. So when we create a notion of a platform, for example, or a notion of a technical space, we are in effect creating a model that reduces the complexity of the actual world of software engineering. That's a very abstract, well, a very complex and very varied world, and it is not possible for you to look at the whole of software engineering. So, in order to construct something you can model or something you can apply your approach to, you end up creating a model. And this is one of the reasons that I argue for the fuzziness in model-driven engineering, because we had to model software engineering, and by means of that modeling, we become, well, we reduce the complexity of the real world, and we had to come up with some kind of pragmatic way of describing the world we are interested in. So that's just an aside, but the key thing really is to remember these three properties of Stachowiak's models. And then another very important seminal figure in the field, again, not exactly of model-driven engineering, but modeling in general, is Rothenberg. And Rothenberg, Rothenberg is more sort of thinking about the what it is that we're trying to do with models. In a way, like Stachowiak, I guess, is a deeper thinker, spend more time. Rothenberg, as far as I can see, seems to apply this more to programming. As you can see, he's talking in the context of AI and simulation and modeling. So slightly more modern thinker. And so what Rothenberg tells us is that modeling, in the broadest sense, is the cost-effective use of something in place of something else for some cognitive purpose. So we haven't really strayed that far from Stachowiak. But this is interesting. It allows us to use something that's simpler, safer, or cheaper than the reality instead of the reality. So in other words, it's much cheaper for you to destroy a model plane whilst doing some tests in terms of, how the plane reacts to winds, different stresses, for instance. It would be much better to do that test using a model rather than a real plane, because, of course, the model is much safer. No one needs to be piloting the plane, and it's, of course, much cheaper. And the idea is that the model represents reality for the given purpose. The model is an abstraction of reality in the sense that it cannot represent all aspects of reality. This allows us to deal with the world in a simplified manner, avoiding the complexity, danger, and irreversibility of reality. Again, very interesting point here. Continuing on the Rothenberg approach, we have a person that dedicated himself to domain-driven engineering. And in domain-driven engineering, models take a central role. The reason why is because in order to talk about the domain, you end up creating a model of the domain. So Evans is really, really sort of significant in this sort of in the centrality of models in terms of software engineering. And so we should really read the words of Evans. So to create software that's valuable, involved in users' activities, a development team must bring to bear a body of knowledge. I mean, we've already spoken about the notion of a body of knowledge related to those activities. The breadth of knowledge required can be daunting. The volume and complexity of information can be overwhelming. Models are tools for grappling with this overhead. A model is a selectively simplified and consciously structured form of knowledge. An appropriate model makes sense of the information and focuses on a problem. So Evans is trying to say is that we're kind of joining the two notions that we've already discussed. The first one is the body of knowledge, this idea of an amorphous amount of knowledge that we've got on a given subject. We don't really know where the body starts or where the body of knowledge ends. There is no formal book you can just pick up and read. The body of knowledge could sprawl across multiple books. It could involve wikis. It's just a set of concepts that you need to master in order to know a certain domain. And what Evans tells us is that if you could associate models with the body of knowledge, then it's much easier for you to understand how the body of knowledge is structured. So these two notions are quite intertwined. The body of knowledge probably defines models, but you can also think of models as a way to structure the information inside of the body of knowledge. So if you take finance as an example, there is lots and lots of stuff you need to know about finance in order to be able to do programming in finance. But what you do when you start a new domain is you start to create simplified notions of all the different terms that you encounter, such as an option, a deal, a book, things like that. And soon enough, you develop a vocabulary that's specific to that field. So within my environment, if I say to anyone a book, everyone knows exactly what I mean. And they don't think of a book like books you see on my shelves. They think of a book where trades are kept. And they think of a blotter as a set of transactions, or way to display a set of transactions, or a ledger that contains a set of transactions, or something like that. And so on, right? And we have all these terms that for us are second nature. If I say vol surface, everyone knows what I mean. And that's part of the body of knowledge. But in a way, those terms are also models, because when we describe a vol surface, we are not explicitly talking about all the details that make up a vol surface. The concept, the model concept, is sufficient for us to, in order to have a normal discourse and to explain and discuss problems. So these two things are very, very closely intertwined: the body of knowledge and the model. But of course, we have to remember that whilst pretty much everything is a model, what we mean by models in model-driven engineering is not just this kind of notion. And to be fair, Evans is talking about the more general notion of models, because he thinks that the vocabulary is a model and so on. He's talking about the slightly less formal way of looking at the word model. But as we enter the more precise world of model-driven engineering, and I say precise in quotes, I guess, we need to move from an informal model to a formal model. The reason being that it's just like in programming, we need to have a certain degree of formality. If a programming language was not formally specified, you wouldn't know when you committed a syntax error, for example. And that would mean that you may have ambiguity in the way it translates source code into machine code, which would then result in potentially incorrect code. And for the same reasons, you can't create a model without having some formal definition of that model, because otherwise the translation of that model to source code would not be would always be ambiguous. And so we resume then the notion of the model and the meta model. So in order to create a formal model, we need some kind of definition, just as with the programming language, we need some kind of syntactical representation of the language. And as we see here, syntax basically is the form. You can think of syntax as, in a programming language, the way you structure sentences, valid sentences in that language. But actually, that's just a concrete syntax. There's also a notion of an abstract syntax. So if you're familiar with programming, you can imagine that for every program you've got, there is the textual representation that you see, but there's also the abstract syntax tree that the compiler sees, in which it reorganizes all the statements you've made into a tree and then traverses that tree to look for validity. So the abstract syntax, so conceptually, you can imagine that you can have any number of concrete syntaxes and they would map to the same abstract syntax. This doesn't really happen with programming because normally in programming there's only one concrete representation of a language. In other words, you don't necessarily need more than one way of writing or no more than one notation for a programming language. However, for modeling, that's not quite the case. Conceptually, you can imagine you could have any number of graphical notations that then map to the same abstract syntax. In fact, they don't even need to be graphical; they could be textual. So these are basically just the concrete ways of representing the language that you're using, and this is what are the fundamental concepts of that language in a way that's not dependent on a specific implementation. And then, of course, in addition to syntax, you also have semantics. And semantics, you can think of it as the meaning. So this is more to do with shape and form. This is more to do with meaning. So in general, semantics are a bit limited when it comes to formal languages because, as you can imagine, there's only so much meaning you can imbue into a language. A computer doesn't know what things are. So meaning is a bit of a strange word to use in the computer science sense. However, you can still think that determining on whether an expression is well formed or not requires some kind of context, and that's what we mean by semantics. We mean that the context is very important in determining the well-formedness of an expression. Depending on where that expression is placed, it may have different meanings. And that's what we mean by static semantics. And of course, then there are dynamic semantics because then that context could change at runtime. However, I wouldn't worry too much about the semantics for our purposes. Just this notion that context is important is probably sufficient. But the two notions together, the notion of syntax and the notion of semantics, are very important because that is how we define a language, in effect, either a programming language or a modeling language. So now the idea then is to try to understand how these things join together. So the abstract syntax and the static semantics, not the dynamic ones, we can ignore those for the moment, they join together to construct a meta model. Now, the way to think about this in terms of programming languages is whenever you construct a compiler, for instance, sorry, I need to cough. Not being very lucky of late. Permanent cough, it seems. So whenever you construct a compiler, you implicitly construct a meta model of the language, as you can imagine, because you need some kind of way of representing the concepts that make up, say, for instance, your abstract syntax tree. And those concepts are going to map to the fundamental entities that your models will instantiate. For example, you should find things like a class, a function, all these entities that define what it is that your language will talk about must exist on the meta model. But normally, in terms of programming, you don't have to worry too much about calling that a meta model. It's just part of the way you could define a compiler. However, if you were to think of this as a more generic problem, you can imagine that it would be useful to talk about these entities in a formal way, such that you can make other uses of those entities, which is something that's very useful in the context of model-driven engineering. In a way, I think that model-driven engineering is an attempt to abstract the process of generating programming languages, if you think about it. And again, we're talking about a revisionist history. I mean, this is not something that model-driven engineering invented. This is just the natural evolution of computer science took us in this direction. And now I'm kind of rewriting history and ascribing sort of intention to model-driven engineering. Model-driven engineering, in a way, is a post-facto thing. It just happened afterwards, and now we're rewriting history and trying to make sense of what it was that people were doing. But in this sort of revisionist history, you can imagine that the natural progression was to go towards this more and more abstract way of looking at things. And originally, you'd create a compiler, you create a high-level language, and so on. You wouldn't think too much about what you're doing, but eventually somebody is going to notice a pattern across all the different languages, and you'll notice that each language has a meta model. And in effect, what the compiler is doing is to deserialize a document which is an instance of a meta model. So in other words, a model. And it's taking that and it's then checking its validity. That's sort of what the compiler is doing, really, from this modeling perspective. And people like Koteman and Konsinsk describe this in a very interesting way. So they said that the meta model captures the deep structure that connects all of the instance models. And the instance models are expressed in the abstract syntax tree of the language, which is the surface structure. So the surface structure is what you see when you're looking at the notation, but internally, inside of the surface, you can imagine that there is this deep structure where the meta model lies. So that's a very interesting way to visualize this. Now, we've already spoken a little bit about the hierarchy in the previous lecture, so I'm not going to spend too much time on this, but there's this notion that we've got the instances in the real world. There's the idea of the model. There's the idea of the meta model, which is the language used to describe the model. And then there's the idea of the meta model, which is how we create meta models. And if we are lucky, we can see this in action here with a classic example. So we can imagine this case, we are talking about cars, I believe. So you can imagine in the real world, we've got, I don't know, a car with the license plate 123 ABC, another one 456 DEG. These are instances of a thing called car. Cars have, in this world of ours here, cars have license plates. So here we're defining all the possibilities for the instances of car. This is a very simple model of car. We're not caring about anything else, the color or the make or anything like that. We just care about license plates. And then you can imagine that there is a way of describing these boxes that we instantiated here. And the boxes are classes, according to our meta model. And there's also a way to describe things like the license plate, which is an attribute, because the attribute will have properties such as a name and it will have properties such as a type, whereas the class probably will only have a property of the name. And those are the meta model concepts. And then finally, one can imagine that in order to describe a meta model such as this, we can get away with a construct such as class, and we can say that, just to be clear, this class is not the same as this class, but these classes can be instantiated, and these are the constructs that we then use to create the meta model. So in this case, there are two classes, the class for attribute and the class for class. And that is the end of our tree, because we can then say that the class is an instance of class. And that's quite nice because it wraps the meta model around. But with these four layers, we can quite easily describe pretty much everything you need to be describing within our modeling world. Now, it's interesting that this notion where the boundaries cannot be crossed and a class in this world is not supposed to exist in the same plane of existence as a class in this world and so on, that's actually called strict metamodeling. But that's actually not the only way to do things. A way to visualize this as a programmer is to think that you can't, in normal code, you can't just say new keywords. You can't, inside of your programming, there is no ability for you to just create a new keyword and get the compiler to reuse that keyword. So in terms of this, what your programming language is saying is you can't just randomly now create a new meta model concept within programming. The reason why you can't do that is because you'd have to go and update the parser, you'd have to update the language, you have to do all sorts of things. But conceptually, there's nothing stopping you from doing that. And in fact, if you're a Lisp programmer, you're used to the workings of macros. And macros are, in effect, a way to extend the meta model of the language. I mean, I'm simplifying here, but the gist is that you can dynamically expand the functionality within the compiler itself and the environment itself, such that new meta model concepts get created and subsequently can be instantiated within that program. So Lisp, in a way, is a programmable programming language, which is not very common because most languages are not programmable. They're programming languages, but they're not programmable programming languages, which is to say, you can't redefine what it means to be a class in C++. It is done, it is created, and that's it. I mean, there's hacks you can do, like you can do template meta programming. And I mean, if you are familiar with the people such as Alexandrescu, which spend quite a long time explaining how you can obtain some functionality that is conceptually similar, but not in practice, to what Lisp has done, you can get quite a lot of mileage from this, and you do a lot of compile time programming. So in a way, in that sense, I guess C++ is also programmable. But strictly speaking, it's not quite true. We're almost what we are trying to do is we're trying to take things like macros, and macros here I'm using the word in the C++ sense, to rewrite text and to create these higher level constructs that then are um, instantiated at compile time into the actual concepts and constructs that the compiler can understand. So in that sense, C++ is not really programmable. We are just um, abusing the macro subsystem of C++, the preprocessor, in order to obtain these facilities. I mean, I'm not saying this is a bad idea or a good idea. I'm just trying to say um, it is not the cleanest way of doing this. Lisp is probably the better way of doing it. But not to get too lost here, what we're trying to say is that there's this notion of strict metamodeling, which is what we normally experience in the normal languages, and then there's this other notion of loose metamodeling. And loose metamodeling is where we got this crossing of boundaries, where you can be inside of one of these levels, and suddenly you can introduce new constructs and reuse them. And there is no reason why you can't make use of a class or make use of an instance of a class at the meta sense. Most of the time, the approach taken by the MD world is to focus on strict metamodeling. I mean, there's lots of diversity and lots of different opinions and so on. So to say most of the time is probably not the right thing to say. But I would say the canonical form I encountered in a lot of my wanderings in the literature is to assume strict metamodeling. But there's nothing wrong with loose metamodeling. It's just that it adds the complexity that you need to know where you are in the levels once you start messing around, such that you don't start to do weird things such as a class, an instance of a class, for example, say car, as a property of type meta class, for instance. I mean, you have to be careful in the way these entities relate to each other. But in theory, there's nothing wrong with loose metamodeling. The other point I would like to make here in my notes as well is I think it is worthwhile for anyone interested in this sort of world, and particularly interested in the history of how this came from programming. You should really read Henderson Sellers, because he does a very interesting history, I guess, of how these innovations, how these inventions came to be, and how they derive from programming and so on. It's actually really, really interesting. So I highly recommend you read that if you're interested in the not just because of MD, but more in terms of computer science. Really, it's quite an interesting read. So there we are. We've got this notion then of formal models. The models have got syntax and semantics. We enter the world of meta models because that's how we describe the syntax and semantics. We know about meta models because that's how we describe meta models. And we have this loose idea that there is an hierarchy of kinds of models. And then we enter the second part, or the second term of our equation, which is transforms. Now that we understand a meta model, a transform should make a lot of sense, because a transform is just a function that takes one meta model and another meta model, and it produces another meta model, and on the simplest case. So the idea being that if you think of something like, say, let's imagine a simple transform that takes a bit of C++ code and generates another bit of C++ code. For example, let's say you're trying to use Clang and you're trying to rewrite C++ 03, which is the legacy version of C++, and you want to transform that into C++ 14, for instance. So you can conceptually imagine that you are using the same meta model. So your source meta model is the same as your target meta model. You can imagine that you have two instances, the programs that, one instance, the program that you're trying to, as the input, and you're going to have an output, which is your target model. And you can imagine that you're going to have a set of rules, which we call transforms, that are going to execute. And what those rules are going to be doing is, they're going to be saying, if you see this construct in my source, map that construct to this other construct. For instance, if you see stud auto pointer, replace auto pointer with, I don't know, unique pointer, for instance. I mean, that's probably not a good idea, but shared pointer, say. As an example, don't take this too literally. And so the idea being that you are creating these rules, and these rules execute inside of an execution engine. And the program that you write to create this transformation is in the language, and that language is the model transformation language. So in our particular case, you can imagine you're going to be writing not in C++, but in some kind of high-level representation of C++ that knows what a class is and what a auto pointer is and so on. So you'd have, in effect, and of course, if you are familiar with Clang, you know what I mean by this. You're going to be taking the Clang source code, and the Clang source code is going to have inside of it a representation of a class, and it's going to have it's going to have an AST of C++. In effect, because in effect you're dealing with a compiler, which is what we've mentioned before, a construct that has to have a meta model of the language that you're processing. And so that's a very simple example of a transformation. Now, if you were to model this or map this to the modeling world, you can imagine that you could have a model, say for example UML model, that contains say classes, and you can have a transformation language that takes that UML model and converts that onto another representation. Let's call it the C++ representation. And so in this particular case, the meta model of the language would be whatever it is that you're using for your UML. And the meta model for the C++ language is, of course, the language C++ model. And the execution engine will be responsible for running the transformation program. And so this generic notion of functions that executes across meta models is very useful. It enables you to, in effect, to do pretty much any transformation, any kind of transformation. I just described a very simple one, which is from source code, or from a diagram to source code, but you can pretty much do anything. And so, due to that, there is, of course, and because we're doing science, there's, of course, the need to classify all these kinds of transforms. So if you're just transforming from a model to another model, you would be doing a model-to-model transform. If you're transforming a model to text, in other words, if you're generating source code, then there'll be a different kind of transform. As we see here, the model-to-model creates an instance of the target meta model. Whereas when you're doing a model-to-text transform, you end up in the realm of strings. So if you go back to our example, I described the proper way of doing a transform that takes a UML diagram over to source code, which would be to have a complete representation of the C++ language as a meta model. But of course, most people don't bother to do that. Most people will just use a text transform language, such as say T4, and they would literally just use some strings, and they would very much like you can do with Inja or Jinja or any template-based infrastructure. You could construct files in the target language without ever having to have a meta model of the target language. And in many, this is something that we struggle with in Dogen. I'm going to make a bit of a parenthesis here. In the beginning, we actually attempted to make a complete meta model of the target languages, C++, C#. And it was actually really, really difficult to do that because, as you can imagine, in order to describe something absolutely trivial in C++, say for instance, a setter, you need a lot of constructs of the meta model. You need a very, very large AST because you can imagine you are dealing at statement level, you're dealing at variable level and things like that. So you need a way to represent each and every of these constructs. Similarly, the mapping between the UML construct to the meta model is also very complex mapping because, of course, there's many entities to map. However, almost always the thing you're targeting is something really basic. So, for example, let's say you're trying to construct a class in textual form. You probably just need the class name, you need the name of the getter, and whether you want the setter as well as the getter and so on. And you can really easily encapsulate all of that in the source meta model with a few booleans and a few properties, and then dump the complexity in the template. And so it doesn't make a lot of sense to have a full-blown meta model, as we found out after implementing a chunk of it, in order to do this simple transform. So what we ended up doing is we ended up replacing our model-to-model transforms, we didn't even know they were called that in those days, by model-to-text transforms. And now we just have a text engine to do that transformation because it's much easier. And of course, there's also very useful text-to-text transforms, which we use a lot. So, for instance, you can imagine you can take, say, a C++ file, and you could indent it, or you could, um, well, you could apply Clang format to it. Um, because this is outside of the realm of the meta models, you're using a separate tool, which we'll discuss later, how these separate tools are modeled. You consider this to be a text-to-text transform. In other words, from your perspective, there was just some text as an input, some black box, and that produced other text. But we are no longer in the world of modeling anymore. And so I think with this, we've introduced the two key concepts, models and transforms. And oh, yes, actually, we probably should talk about empty chains. So most of the time, transforms are bundled up into groups to do certain work. So you'd have a top level transform, and that transform is then composed of a number of transforms, which could then be also composed of a number of transforms. And what we normally call it is top level transforms, like the composite transforms, if you want to call it that. We call them model transform chains, or transform chains for short. And the idea being that you execute these chains as if they were pipelines. And you can then imagine that there's graphs of transforms that are logically related to each other, so that you could say first you must run this transform, then you must run another transform, and there are dependencies between the transforms. Um, but conceptually, really, we're still talking about transforms. It's just that there's this notion that some transforms are leaves, in that they just execute, and other transforms are composite in the sense that they're composed of loads of other transforms. And this is kind of all the concepts that you need to know in terms of transforms at a high level. And finally, we just have a quick look into the kind of applications that we have for transforms. So these are all model-driven engineering sort of applications. So some of them will be slightly high level. I won't be able to explain them in great detail because they require a lot of knowledge about the subject, but we'll just rattle through them. So for synchronization, well, synchronization should be more or less obvious. If there is a target model and a source model, um, and we apply the transform, there's always going to be a point in time in which the target model is not in sync with the source model. Um, so we require running the transform in order to synchronize the two models. So as an example, imagine that you've got a representation of a model in UML, and then let's imagine that you take that representation and then you create source code. So the synchronization is the notion that different models need to be in sync. They need to be the two representations correspond. No, the representation of the first model corresponds to the representation of the second model as by the application of the transform. This doesn't make a lot of sense in this sense. You may be thinking, I mean, doesn't that just mean run the transform? But the notion is that we there's this idea that we can do cascading with models. I'm just going to skip ahead a little bit so you can see what I mean by this. There's this notion that models they exist in a cascade. If I could find the diagram. Unfortunately, I don't think. Here we go. So there's this notion. Up to now, we've been thinking about very close to the implementation level. But model-driven engineering is not limited to that. The notion of model-driven engineering is that you're going to cascade through a series of abstractions at varying levels, and you're going to be transforming from one level of the abstraction ladder to another. So you conceptually can imagine that you start off with the requirements model, and you apply a set of transforms, and that requirements model can then produce an analysis model, and that analysis model can then be transformed via a set of transforms to produce an architecture model, and that can then be transformed subsequently to produce a component design and so on. I mean, this is a very exaggerated example, but conceptually that's what we're aiming at. So there's this cascading of transforms from one high level of abstraction to another lower level of abstraction. And so synchronization makes sense because if somebody does a change, say the requirements, there is a need to synchronize all the way down to source code. And that's what we mean by synchronization in this complex topology of models. But we're not going to get too much into that because it's it's a little bit complicated. So we will require a bit more concepts to understand how they all hangs together. Um, where were we? I'm a bit lost. Right, here we are. Querying. So you can imagine that you may want to generate views over a system. So you may want to get a subset of a model, or the transform is used just like SQL is used to perform operations on data. You can imagine a transform language that allows you to do something equivalent. Evolution is related to the versioning of models, and how models evolve over time. You can imagine that you may end up with a version 1 of a meta model, a version 2 of another model, and you can have a transform that enables you to convert from version 1 to version 2. And similarly, with reverse engineering, you can imagine that you may want to take something from source code and generate a model, and vice versa, according to that cascading that we just described. And finally, of course, the most obvious use of models is code generation. So you can imagine, I mean, from a perspective of model-driven engineering, there is a lot that transforms do, and this field is very large. It's very, very large. And there's many transform languages. So as an example, there's QVT, there's the ATL, or Atlas Transform Language, Epsilon, Kermita, and many other languages. Some of these languages are related. Some of the languages are completely different in terms of genealogy and how they're used. They have different purposes. And one of the problems you find, as with pretty much everything in model-driven engineering, is it's very difficult to make heads or tails of the body of knowledge in the beginning, because there are so many options and so many different languages that it's not entirely obvious what you should be doing for your particular purpose. And worse than that is you may end up needing many languages in order to create a product, because of course you don't need just a language, you don't need just one set of transforms. Perhaps you need one language to enable you to generate model to text transforms, another one perhaps for querying purposes, another one perhaps for evolution. So you can imagine that you could end up in this sort of Babel tower of languages, and some very confusing scenario where there's lots and lots of different modeling languages, and that's not ideal, really. And finally, as you can imagine, if you write a lot of this code, I mean, at the end of the day, these transforms, whether they're graphical or textual, at the end of the day, they're like source code. And so you're going to end up with things like technical debt, refactoring problems, and difficulties around reuse. So the more code you write using these languages, the more you will end up with the exact same set of problems that we've got with regular programming. So finally, for our lecture today, we'll just very briefly describe these differences between general purpose modeling languages and domain-specific languages. So in fact, to be honest, let's just take a step back here for a second and just go back to programming languages versus modeling languages, which actually is a little bit further down. So the first thing is, in a way, as with many concepts in NDE, these are not definitions that are set in stone. I'm not trying to say that these are relative definitions. So what I mean by this is, if you were to call a programming language a modeling language, you would not actually be factually incorrect, because in a way, programming is modeling. You are modeling the world. What we're trying to say, though, is that there is this notion of intention, I guess. What we wanted, the relationship between a programming language and a modeling language is such that the intentionality of the modeling language is to distinguish between the programming process and the modeling process. To state quite clearly that when we're modeling and we're programming, such that the programming activity is a lower level, in terms of the abstraction ladder, a lower level activity, whereas the modeling activity is a higher level activity. That's what we're trying to say when we try to distinguish between programming versus modeling. I mean, there is definitely a case to be made that programming and modeling are the same thing. But if you do that, then suddenly everything becomes modeling, and now you can't really describe the issues that you deal with at higher levels of abstraction. It's a bit like saying that programming in C++ is the same thing as programming in assembler. I mean, yeah, it is true, we are programming, but there's something qualitative happens when you raise the abstraction level. Something. It's not just the quantity that changes; it's the actual nature of the process changes. Um, Something fundamental changes, and that's what we're trying to say when we're talking about distinction between programming languages and modeling languages. And I think we try to make that point here. And so then we can think, well, but there are, even within modeling languages, there are two kinds of modeling languages, really. There is also this notion of general purpose modeling languages. So, for example, UML is one such general purpose modeling language. But then you can imagine that you can construct a special purpose modeling language. And normally we call those domain specific languages. Again, you could say, well, isn't just a programming language a domain specific language? Yes, if your domain is programming, presumably that would be the case. These definitions cannot be taken as strict definitions. You have to use a lot of common sense in order to interpret these things. And like we said before, this is a modeling exercise, so the definitions are only useful if you use them in a pragmatic way. You can't use them in a strict, abstract, absolutist way like you do with maths. These are not formal definitions that will be applied like mathematical definitions are. So if I say to you a DSL, I would have to give you the context of what I'm trying to explain, because a DSL could easily be something you created within a programming language. And it is perfectly valid for you to say that that's the case. But in this context, we are thinking more, let's imagine I created a model that enables you to create financial products. You can't do anything else because the atoms, the entities which we're going to be dealing with are only financial entities. So instead of a class, you have an option or a forward or a future, which means that the language will not allow you to escape the domain. You're stuck with that domain. That's what we mean at this level for the DSL. And I think that's probably going to be it for today, because I would like to spend some time talking about the problem space and the solution space. So just to summarize then what we've done today, we just spoke a little bit about the two fundamental concepts that exist in model-driven engineering, models and transforms. And as we said before, transforms are actually in models as well. They're just a different kind of model, a model that's used to convert from one model to another model. But just like models, they have to have a meta model, and fundamentally they're similar in terms of their nature. And with these two things together, and via the process that I described, the cascading of transforms across abstraction levels, we can start off from a very, very high level representation of the software system, and we can go through all these layers of transformations, and we'll end up with some kind of system, a software system that can run and can do what users expect it to do. Now, again, we will talk about why it is that you can't just do that in practice, but let's just stay at the theoretical level for this chapter, and probably for a couple of chapters, I think. Okay, that's all for today. Thanks for watching.